Cool. And then also,
Nope.
Ling, I have it still on my to-do list. Let's see, did my face freeze? Can y'all still hear me?
We can hear you, but
Can
you're
still hear you. Yes.
Yeah, this happened. This tends to happen with my camera. But Ling, I still have it on my to-do list to go through um, the GitHub and kind of troubleshoot what works as like a new member to that.
Okay.
okay.
So
Cool. All right.
still on my back burner.
Perfect. Well, let me welcome folks who might be tuning in. Welcome to the new, now public weekly Epiphyte meetup. Epiphyte is a project of the Open Air Collective that basically we're designing a miniature desktop direct air capture machine that is open source. And the idea is to continuously improve that and take it into new directions as we go with more and more people, hopefully all over the world. And so just a bit of background for newbies is we started this project that kind of organically arose over many, many months here within Open Air. And we finally really got to, all right, well, let's do a design. And we based it on a prototype that was developed by the Kenya-based DAC company Octavia, which is very close to Open Air. And through that, we kind of modified it for our purposes and optimized a few parts of it. And then in Philadelphia, led by David Wilson, you see on the bottom right-hand corner of your screen, we went ahead and built that prototype at the University of Pennsylvania's Department of Engineering and Biochemical Engineering. And that took place over the fall and into the winter. And we made it. And this is a picture here, which I'll just show you. This is the A picture. You can see it's the direct air capture unit sitting on top of bolted onto a cart. And we went ahead and finished that, and we had great results. And what we tried to do is have basically our hello world build. The idea is, can we build just a simple functional unit that we can put online, publish under open source, and then go from there? So it's a kernel, if you think about it in software terms. It's the most simple sort of thing. And what we wanted to do is just be able to document some, however trivial, amount of carbon removal that actually happened. We achieved that goal, but in the process of building it and testing it out, we realized, oh, there's a lot of things we would do differently or things that we have to optimize for. So what our team is doing now is over the next few months, we're going over each of those optimizations and going to come up with solutions to them that can then be folded in together and be the basis of a second build that we'll do this summer. So in order to be effective, we have our amazing team here from various parts all over the US and in Europe. We really want as many eyeballs on this as possible. So as we're talking through this, I'm going to drop a link in a second that gives you kind of a brochure. Actually, I'll put it in there right now. This is the very simple website as we're getting some fuller documentation. Let me put it in the chat. I don't know if anybody can see the last one. That really kind of lays out everything you sort of need to know about where the project currently stands, including the optimizations that we need to go through. It goes into what future development might be, other things that we want to work on with Epiphyte. So if you have that, that's a pretty good package for you. It includes a bunch of links for how you can join our discourse, how you can participate in our forum, a little building a bill of materials, which David tells me I have to tweak a little bit. But all of those things are on there. So what I thought I would do is real quick, let me just introduce the team. You guys want to say hi? I'll start with Ling and go clockwise. Oh, can you?
Sorry, I was on mute. Yeah, my name is Ling Kong. I'm a biomedical engineer by training. I mostly worked on hardware for many years, mainly microfluidics. And then I did mechanical design to various degrees. And then now I work on software, actually. So I've been here in Open Air working on like various carbon capture endeavors for, I think it's about 2 years now. So I kind of just like pitching wherever I can. Yeah, I'm happy to help. I did the latest design for, well, I did the CAD part. I didn't really do the design for the sorbent panel, but you know, like I pitch in where I can.
Perennially, in her modesty, she always sells herself short. But we got to say, Ling is sort of the is one of the glues that holds this whole thing together, and really has been involved from the very beginning. So thanks, Ling. And David, man in Philadelphia.
Yeah, I'm David Wilson. I'm an electrical engineer, and I worked on several aspects of the Epiphyte, but mainly the electronics panel, the software that runs it, and the sensors, and also the heating elements. We also had some other team members. Ling, in particular, worked remotely, and a couple of others that had to eventually drop their involvement because of work reasons. But yeah, we're hoping that this thing can keep on going, and that there will be another build. I've been involved with Open Air for about 3.5 years, I guess. I started on a project called SciM, which was a very simple, like tabletop CO2 capturing system that could be built in a couple of hours. That's it.
Yeah, and David was really the straw that stirred the drink in Philadelphia for the first build, along with a few other folks. So he's been absolutely key. And then we got Ben, our American in Paris. Ben, can you hear us?
Yes, I can. Let's see. I'm gonna try one more time.
There you go.
See if my camera works. Nope. Yep. I love how my camera will turn on for maybe 2 minutes and then break. That's super fun.
All right,
But,
let me know what it looks like.
Yeah. So hey, I'll put up my little picture there. Ben Evanson. Yeah, been working with Open Air. Started a organization at the University of Texas called the Negative Emissions Technology Project. Started getting really involved in the space 2018, 2019 when it kind of was first picking up traction. So just have been so excited to see like a whole industry kind of emerge from that, and just love working with all the carbon removal people because it's the most collaborative industry that I've ever worked with, and maybe it's too young to call it an industry yet still. And I fear for the day when it does not become so collaborative, but knock on wood, I hope it remains to be as such for the rest of its entirety. But yeah, I've had some experience. I currently have a sculpture on exhibition at the Duende Museum in Foshan, China. The sculpture is a functional direct air capture device feeding concentrated CO2 to a series of algal photobioreactors. And I'm currently working at a venture capital startup accelerator, climate tech startup accelerator in Paris. And so, part of my job is evaluating carbon removal startups and ideas. So super excited to kind of be continuing to work on and develop direct air capture, especially from a grassroots stage. I think that's the most fun part about this.
Awesome to have you. We'll be tapping your brain shortly because today we're going to be talking about our sorbent upgrades, and this is ground that you traveled obviously quite a bit
For sure.
And then we have Tim, who I'm not sure if you're in New York right now, but I know you.
Yes, I am. I'm in New York. Thanks, Chris. Yeah, I'm Tim Gazal. I spent most of my career as a hardware engineer, and with a bit of data science in the mix. I actually did very different things in the past. I used to work on cameras and spectrographs, but you should never let having worked on completely different things stop you coming and trying something different. So I've just joined the Epiphyte team and trying to make myself useful by doing a few calculations to figure out how we're going to all make it better in the future and optimize everything.
Yeah, awesome to have you join, Tim. We do have other folks too. Some can't get on right now because of tech problems, but great team, very different disciplines, nicely spread mostly throughout North America, but hopefully globally soon. So what I'll do is I just want to quickly show you a little bit more context here, which we can, I will open up this screen here, share, and this, and hopefully you see that. And I'll go ahead and make it full screen. So where we are right now is, again, as I said, we want to kind of solve for some of the issues that we faced through the first build. And these are, David originally listed them at the end of that build, but I kind of split it up into a couple more pieces. And there's 8 of them, and I'm not going to go over all of them now because we're going to focus just on one today. But the idea is to go in order with input from this team and from people watching and on our forum to try to figure out the best approach to solve these, so that when we do a new build this summer, which might be in a couple different places, it might be at UPenn again, could be in New York City at NYU, or potentially where I am here in Austin at University of Texas. But what we want to focus on today, which is really key, is the sorbent upgrade. And the sorbent is somebody, you'll notice for me, I'm the non-scientist, non-engineer, so I keep things very, very simple. But for folks who are just tuning in, I'm wondering, Ben, if you just want to very, very quickly just say, what is a sorbent and what does it do in 15 seconds or less?
For sure. My analogy, my go-to analogy is the sorbent is a CO2 sponge. So if we parallel it to a water sponge, instead of soaking up water, it soaks up CO2. Hopefully, it also, some of these soak up water too. But at some point, that sponge will get saturated after soaking up a certain amount of CO2, and then you'll squeeze the sponge through what you either call a temperature adsorption swing or a pressure adsorption swing. So typically, you either change the pressure or the temperature. There are other methods of swinging a sorbent, and that squeezes the sponge and releases the CO2. So yeah, that's the basic idea.
That was really, really good. And we will talk about the water thing. That's more than a metaphor in our case, unfortunately. So, but what we did initially, if folks have any questions or ideas or stuff like that, just throw it in the chat and we'll wrap it right in. You guys are as much a part of this as any of us. We're trying to, again, grow the number of people thinking about this. But what we did initially is we went with a type of sorbent that's a zeolite-based sorbent that we bought from Sigma Aldrich called a molecular sieve. And we knew from the very beginning that that was not going to be a great sorbent. It was just that one that we knew that we could get our hands on and test out with to hopefully get our hello world signal. But after looking at the results, and they're all summarized in that brochure that I shared, you can even see a little video of David talking for a few minutes about what problems we sort of faced. We realized immediately, like, yeah, it's time to move on from this and look for another option. So by changing that sorbent, what we're trying to do is at a good cost, good energy, to maximize or increase the amount of carbon that we're absorbing, and then also increase the efficiency or performance of the desorption, so getting it out of the sponge. And we're shopping around for a few things right now. We're going to talk about that because Ben has a lot of experience with it. Tim has been doing some number crunching, and David saw firsthand what the limitations of the original sorbent were. And maybe, David, if I could, if you want to just maybe just in 30 seconds or so again, just sort of define what the limitations of the initial sorbent are, why we're moving on.
Well, the main limitation of this chemical, the 13X, is it really likes to absorb atmospheric water as well, preferring it to CO2. So unless you have an intake that is completely dry, it's going to absorb water, and the water is going to fill up all the available slots, so there won't be room for any two molecules. That very much limits the efficiency of it.
Yeah, and then Tim, you even did a little bit of back of the envelope or even Google Sheet sort of analysis of its inefficiency compared to the new sorbent we're thinking about. And I didn't know if you had any top lines from your first sort of swipe at that you want to share about how crappy of a sorbent it actually was.
So I think one of the things that was quite instructive was that oftentimes, this sorbent, the reason we came across it was because it is actually used to pull CO2 out of the gas streams. But the main problem is that typically it's used for if you were going to try and pull CO2 from a process where it's got loads and loads of CO2 coming out of it. So for instance, maybe from a power plant, whereas what we're trying to do here is pull CO2 out of the atmosphere where it's much less concentrated. And so that's where the problem that David brings up comes into play, because when you've got atmospheric air, it's got less water vapor in it, which screws things up for you. So yeah, always helpful to go through and do some calculations and actually figure out kind of what the optimal choice of thing to choose is. And I think we'll go through that process now. I think Ben's got a secret spreadsheet where he's done a lot of this work already. So hopefully he'll give us some pointers.
Yeah, unfortunately, I've been keeping it a little too secret. I'm figuring out still where I should share it. we can talk about that logistically more later, but go
Yeah,
for
we
it.
can. I think we can kind of talk through just what your experience was. But what I will do for folks is go ahead and it's in that little brochure on the last page that I shared. But I will also put this is the Epiphyte forum where we both tracked David very sort of in a very disciplined way, tracked through the results of our first build. But now we're adding forum posts that relate to the optimizations we're trying to achieve. So we have one going right now around the new sorbent we're thinking about. And Tim actually did, I believe, Tim, you linked even you may have linked your spreadsheet there. You had some feedback, but if folks want to geek out on sorbent and provide thoughts or ask questions, that's a good place to do it. All right. Now let me share one thing here quick. And if we can think, I'll just give you the history of what one sorbent that we are considering, again, that I just showed you the picture of, is this one, Epiphyte, PPOC 1065. And this one was recommended to us from a friend of the project, Dr. Susana Garcia Lopez at Heriot-Watt University in Scotland. And she is working on a really cool thing that you'll hear about if you stick around in the Epiphyte project. It's sort of a machine learning sorbent discovery platform called usorb. But she said, well, why don't you do this one? Because this is one that they use a lot in CCS, carbon capture and sequestration. And there's some pretty good documentation on it. So we started to look at this, and the form of it seems to be aligned with the way that our machine is built. But we're not going to go ahead and whip out the credit card and buy it yet until we think through it a little bit more. Do you remember we had a couple people that were a little more fluent in sorbent than I was last week? I know, Tim, you did look a little bit at documentation for this, but I think the main thing that we like about this is that it wouldn't be so, what is it, hydrophilic? It wouldn't absorb water and preempt carbon absorption. But I think there are a couple of other advantages there. And if anybody smarter than me wants to name them, now would be a good time.
No, I think that's pretty much. I think that's pretty much it. Actually, I mean, we basically, I think this hydrophilia, almost hyperphilia, no hydrophilia, makes the 13x almost, useless. Whereas the Civitate just doesn't have that problem. So, an immediate kind of 100x improvement.
All right, we like 100x improvements. They don't come around that often. So that's the leading contender here. But we want to be, one of the things that you'll see looking at the document and as we get into future optimizations is that we actually want the machine to be something that it's relatively easy to swap out sorbents, right? So if over time we discover a new sorbent that we want to be the main sorbent, we'll put that in there. But this device and the way it's built and the cost of it and the ease of use, we hope will also make it easy to actually test out different sorbents, that there's not much of a penalty of deciding, saying, I want to put this sorbent in there and see how it works. So that's part of the mission, because the sorbent is really the secret sauce. But what I thought we could do now, because Ben, who I was well connected with here in Austin before he moved to Paris, as he said at the beginning, created his own small desk scale direct air capture machine. And a lot of the work he did was exploring, well, what are my best options for this? So I thought what we could do is have Ben sort of give us some top lines about what his process was and what he found, and if he's actually familiar with this particular sorbent that we're considering, or if there's something else we might want to look at. So, Ben, with that, I'm wondering if you could just, share away.
No, for sure. I have a couple. I pulled up kind of like all the documents that we've used to analyze this before. I guess I kind of want to first ask the group how familiar everyone feels with the sorbent space, because I don't want to lecture over anything that's familiar already to us. I guess I'm hearing from Ling, David, Tim, kind of what's our general knowledge there?
I only know basic ideas of sorbents.
Okay.
I'm able to do chemical calculations, but not that familiar with different sorbents.
Okay.
Yeah, I could certainly use an update.
Yeah. Okay. Cool. All right. Cool. Yeah. Well, Chris, am I able to present screen here? Because I have a couple different documents, and we can figure out later the best way to consolidate and post about these documents and kind of refer to that.
Yeah, I'll just put them on the forum for you, Ben, or guide you to do that later today. So people.
Okay, cool. Because yeah, I can post them directly. I was trying to do that as a reply, and that wasn't working super well. But the logistics, yeah,
We'll
can
figure
tune
it
out
out.
later.
So on the bottom there, right below all the faces, there's a present box in the middle. Just click on that, and it's pretty self-explanatory from there.
Cool. Let's see.
We have 21 people tuning in, so I just want to say hi, world. This is being projected out to LinkedIn, X, Facebook, and our YouTube channel. So
is everyone is able to see my screen here?
I'll go ahead and add it to the stage, and there we go.
Cool.
Yes.
Is this also sharing the presentation now?
It's showing. We can see the main slide. It is showing the slides on the side. If there's a full present mode, go for it. But we can live with it.
Okay, yeah. Let me go to full present. So cool. Is this everyone can see the sorbent classes slide here?
Yep.
Yes.
Cool. So yeah, I mean, this is kind of how we sussed out the field a little bit. And there's certainly things missing here, but this was kind of like a good rough outline for us. And yeah, this isn't any degree of a fancy graphic or anything, but something we put together. But yeah, so within sorbents, right, we have solid sorbents, right? Sorbent refers always to solid, and then we have liquid solvents. So your kind of two top contenders are Climeworks. They work with a solid sorbent, and yeah, just recently announced their headquarters in Austin, Chris, which I found out the other day, which is awesome. But yeah, so Climeworks is an example of solid sorbent. On the other hand, Carbon Engineering is an example of liquid solvents. Since the DAC field has kind of matured, it seems like solid sorbents have kind of taken off. And then we can kind of like, there's redox mediated electrochemical sorbents, which is a company like Verdox typically works with. And those kind of peer into a realm that I'm not super familiar with, but can be really interesting. But for a simple DAC device, solid sorbents are kind of your most classic things to work with. So within that category, there's three different main families. You have physisorbents, chemisorbents, and moisture swing adsorbents. Moisture swing absorbents are kind of the original Klaus Lochner, who's a researcher at ASU, who's to some degree credited as the father of director capture as a field. Those are sorbents that typically a lot are associated with his kind of research, and those get really in the weeds. I've never super looked at those. They're a bit tricky to work with and synthesize because you have to have a completely dehumidified airstream coming in. And even though our adsorbents are picking up some amount of water, right, like those are really, really tricky with their water reactions. And so, yeah, we focus then kind of on physisorbents versus chemisorbents. The main kind of differences, pros, cons between those. Physisorbents, right, is just a physical interaction. It has a pore size that's perfectly suited for CO2, and CO2 will just sit in the pores of physisorbents, versus chemisorbents actually react with CO2. What that means is there is a higher energy penalty to regenerate chemisorbents than there is for physisorbents. However, chemisorbents will have a much higher capacity in attraction for CO2. Is that kind of first explanation make sense for everyone?
Yes.
Yeah.
Cool. Within physisorbents, we've probably heard before metal organic frameworks, MOFs, zeolites like zeolite 13X, like we're working with, activated carbon, and then there's some others. We, within our research, kind of moved away from physisorbents just because the working capacity, the amount that of CO2 at low partial pressures that these adsorbents are able to pick up is super low, and trying to work with that is pretty difficult. And we'll show some math later kind of related to that. But yeah, so we moved away from physisorbents pretty quickly and moved into chemisorbents. Within chemisorbents, the way to kind of understand those is you have two things typically. And there's other kind of chemicals that react with CO2, but the most common are your amine-based chemicals. And those amines need to be functionalized onto a backbone. So you kind of have a kind of mix and match of Lego pieces here. you can have different kinds of backbones, and you can functionalize them with different kinds of amines. When we look at Liwetits, that is a resin-based amine. I can't remember what it's functionalized on. I think it actually may not be functionalized on anything. I think it might be a solid resin. But yeah, something we can dig into more. But you can have carbon, silica, or alumina-based backbones, and then in your amines you have secondary, primary, secondary, and tertiary amines. I'm a mechanical engineer. The differences between those things are a little beyond me, but once we really start digging through the literature, if that's something that we're interested in, that'll matter later on. Before I move on, is this too in the weeds? Are we feeling okay here, Chris? Does this seem relevant?
I'm not the guy to ask because I haven't taken a science class into the 11th grade. But if these guys are understanding it, then well, I'll let them. Well, let's pause for a second and see if there's any feedback on any of the main concepts.
Yeah.
So I think it's a pretty clear summary. What sort of swing do the chemisorbents, particularly the amines, use? Do they also use temperature, pressure?
Yeah. So pretty much all of these can be swung. Definitely all of them can be swung by pressure. The reason for that is, let me see if we have a model of this. Yeah, so this kind of explains general isotherms. The reason that pressure swings just about any adsorbent is that sorption is just simply a function of the partial pressure of CO2. And that just refers to, kind of how much CO2 is in the atmosphere. For our cases in atmospheric conditions, it's 0.04%, 400 parts per million of CO2. So you can pressure swing just about anything. Sometimes it's not the largest pressure. You don't really get the largest differential there. But we can see on the left here, and again, this has been a while since I've gone through this. But if we look on the left, that is a pressure swing happening right there. And then on the right, it looks like a pressure swing, and on the left, it looks like a temperature swing. And so, that's all that's trying to describe there between those two graphs is like you have different kinds of isotherms, which is that kind of line at 40 degrees C or a higher temperature on which you have different adsorption loadings. And then when you go to, I wish I had a better version of an isotherm, but when you go to a different temperature, you lower that sorption capacity, and the difference between those two sorption capacities, which are a function of pressure and temperature, that difference is your working capacity. And that's true for pretty much every single physisorbent and chemisorbent. So it gets a little different when we talk moisture swing adsorbents, but not so much. And then very different when we talk about redox mediated sorbents. Any other, and also this is what I remember and what I learned. Please push back. I shouldn't be talking like I'm an actual expert on this.
Can you, Ben, this is great. Can you talk a bit more about why I'm sorry if I missed it, why you decided that physisorbents weren't the way to go? Is it just because that's much less effective?
Yeah, that's a great question. And this is, so there's another, that we're in our presentation mode right now. There's another spreadsheet that we can go through. And actually, let's see. I also can't see you guys' faces right now, so I'm feeling, oh, there we go. It's a little hard to kind of present with no feedback, but we'll go. I'm sure you guys are familiar with that, right? Like presenting to a blank screen is kind of intimidating.
Yeah.
No worries.
We're all ears. We're all paying attention.
Sweet. Appreciate it. So this is a mess. We're not going to stay on this for too long, but this is our original calculations with one of the kind of most eminent physisorbents out there called CALF20. I can't remember exactly what the chemical composition of CALF20 was. We just kind of like worked off of a couple papers, and this is under the guidance of now a postdoc in Chicago at UChicago, James Burrow, Dr. James Burrow. he was like, hey, like his background is in CCUS, like chemical sorbent capture. And obviously CCUS versus DAC, we have some pretty serious differences, being that in CCUS you can use physisorption because your partial pressure of CO2 is around, like, I don't know, you can get up to 14%. In direct air capture, you're at 0.04%. You have to have way higher reactivity and selectivity in direct air capture as compares to CCUS. And so he referred us to a physisorbent that's just, you know, kind of one of the best for CCUS. And so we investigated it a little bit. And roughly what we're looking at here, maybe we can tune in on this little graph. Right now, none of this means anything to anyone, including me. It's been a while since I've looked at this, but maybe we can go for this one. Okay. So we can see in blue, this is
Can you enlarge that a tiny bit, Ben? Just to like stretch it down so it covers up the other stuff. There we go.
Yeah. Sorry, you said stretch
move
it
it over.
out.
Yeah, I think so. Then move the other thing. Just so
It
we
might
can-
be.
Yeah,
It might be
let's-
more. It might be better if you zoom in
There you go.
Excel.
There you go.
Yeah, that's Ling, that was a way better idea than trying to just block everything else. But thank you. So yeah, we have kind of three lines here, right? Our blue line refers to the adsorption capacity for CALF 20. And again, that refers to at your adsorption pressure and temperature. On the right, this is how many moles per gram of sorbent it's picking up of CO2. So we can see at 400 parts per million and ambient temperature, we're incredibly low, right? Like what you want for that ballpark grams per mole, and correct me if I'm wrong, Tim, but Lewitit is around, it's a little less than 1, maybe a little bit more than 1 grams per mole, or moles per gram of Lewitit. Is that correct?
Yeah, I think it's a bit under. But we're also, as you say, it's very dependent on what the partial pressure is. And at least from what I did, it was all done at very high partial pressure, so I had to extrapolate. So I could be completely off for the numbers that are relevant for atmospheric CO2.
What do we have? Sorry, I know I'm skipping through things here. Yeah, I think. Okay, no, so Tim, you're totally right. It's like 1 millimole of CO2 per gram is kind of what we're working with. So, and so go for it, Tim.
No, go ahead.
Yeah, hopefully I'm correct on that. Again, it's been quite some time, so there could be some flaws here, but I believe, right, what we're seeing on the y-axis is the millimoles of CO2 per gram uptake. So I'm backtracking on saying moles. That's a pretty big difference. But roughly what we came to is that Q absorption, the amount that it uptakes, super low. When we increase, and I think we're working with, on this one, this is our best case scenario. So we're modeling desorption at a super reduced, let's see, adsorb from air at 20 C, desorb, and we're adsorbing as well under high pressure and desorbing under low pressure. So suffice to say, this is kind of optimal conditions desorption. So let's say 150 degrees C desorption, super low partial pressure of CO2, or just super low total pressure. We were only able to get a positive working capacity when we were desorbing at above 300 degrees Celsius. I'm not sure if that explanation totally made sense, but what we're seeing on the x-axis is an increasing desorption temperature, and that gray line represents the total working capacity, the difference between your adsorption capacity and your desorption capacity. And we're only ever able to make it positive in this scenario when we move to desorption past 300 degrees C. So that's kind of that's my long short of explaining why physisorption didn't work. But this is one of the best physisorbents out there. Metal organic frameworks are a bit of a different story. You can make those potentially work. They're just pretty difficult synthesis procedures. You need a pretty advanced kind of chemist to be working in a wet lab on this. not many are commercially available to buy, and those precursors tend to be very, very expensive. And Chris, we can talk about it. The DAC project is currently trying to synthesize them off because we have kind of Will's expertise and got a little bit of funding for it. And we'll see how that goes, but certainly there's still some suspicion there. So yeah, how's everyone feeling?
Good.
Okay, cool. Any questions still thus far?
David, did you have anything to say about the actual physical system that we built and some of the parameters that are also important about how we use it in terms of heat and stuff like that? If not, that's okay. I just didn't know if there's anything you wanted to.
Not at this point.
Okay.
Okay, cool.
That's good.
Sweet. It was just nice to see everyone's face here for a second before I go back into things. But okay, cool. Chris, should I continue on here? I have a little bit more on kind of how we compared our different sorbents and the different sorbents that we actually ended up looking at.
Well, let's do this. I think that would be great if others want to hear that, and we can make that quick, and we'll obviously elaborate on it in the forum, which I did provide a link to. And definitely eager to hear what you wound up landing on and why, and what you think of the sorbent that we're thinking about currently in comparison to the one that you landed on. I think those are the main pieces. Go ahead, David.
And can you please provide a link or upload these slides?
Yeah, absolutely. And right, Chris, on the back end, we'll kind of figure out how to share these different resources.
Yeah, I'll get it up I have a couple more meetings after this, but I'll get it up by this afternoon CST. So anybody who goes there will be able to see those resources.
Cool.
So.
Are we able to see my slides again?
Oh, let me go ahead and add that. There you go.
Sweet. Cool. So yeah, we needed to do some thinking about this all together. I can't remember exactly. It doesn't make a ton of sense in my head at the moment why the desorption capacity is ever higher than the adsorption capacity here, right? It's kind of a sliding scale there. I need to remember exactly. I need to remember exactly why that's the case, but we'll move on for now. We can get in the weeds another time. So this kind of refers to, I might go to the actual Excel sheet here, but this is all the sorbents that we landed on as kind of like our favorites. And again, I apologize for the spreadsheet nightmare here, but you can see kind of at the top, Luatit was one of our top contenders.
Okay, good.
It has a pretty decent working capacity. And again, we'll have to double check this, but we calculated it to be 0.4 millimoles of CO2 per gram of sorbent. This is at the kind of working capacity of 400 parts per million, 30 degrees Celsius, and a temperature swing of around like 100 degrees, like going up to 130 Celsius. And so that's kind of the working capacity that you're able to get there. We calculated its water uptake. It uptakes still a significant amount of water, but it doesn't necessarily interfere so much with absorption. A funny thing about amines like to have a little bit of water adsorbed to preferentially increase the uptake of CO2, but there's a trade-off, right? It can take up a little bit of water and that'll increase the CO2 absorption to a certain point, right? You can't have too humid of a stream or too dehumidified of a stream. There's kind of like a perfect mix that you got to use. So that means that like geographical location with humidity can be important. The big thing that limited us on all of our sorbents is the temperature before degradation. And this refers to degradation by oxygen. And so, right, like our system did not have a depressurization for our desorption cycle. And that means, and the main kind of benefit of that is to try and remove as much oxygen from that system as possible, as well as assist in the absorption capacity swing. But that's a huge benefit that Epiphyte has here, is that kind of ability to depressurize the system. And right, the main benefit is just trying to get as much oxygen out of there as possible, because every single amine under high temperatures is going to start degrading in presence of oxygen. So that was kind of a big killer for us. So yeah, Luatit can be really interesting, decent cost, right? It's purchasable. We liked it a good bit. The reason that we moved away from it, and I'll hopefully go through our TGA results. We did a thermogravimetric analysis of a couple different sorbents, but our other kind of top contenders, we can talk about all the ones that we looked through another time. But fumed silica and PEI was kind of our next best top contender. The backbone there is fumed silica, so that's nanoparticle silica. And then we grafted polyethyleneamine, very standard amine adsorbent, onto the fumed silica to kind of make this like particulate, it's kind of like a hard particulate mass. And that was kind of our next best contender. This is what we ended up running with. And I'll show kind of our ultimate analysis of this. Yeah, we also looked at, the other thing we looked at is nanofibrillated cellulose and Apdes, which is just another amine. Can't remember the full name of it. That's roughly what Climeworks uses as their sorbent, is Apdes and NFC. And so we studied that as well. There's some interesting benefits to that. The first one being NFC is a organic based molecule. So you have some reduced carbon embodied emissions for your sorbents, which is huge when you're doing a large scale DAC facility in which you're processing and sometimes losing. You're not fully regenerating. Sometimes you're degrading your sorbents. You have to replace it, and it has embodied CO2 emissions. So an interesting kind of thing to work with there. But to create that NFC Apdes, I mean, there's a big synthesis procedure. Again, Luatit's off the shelf. That makes it a lot easier. So this is kind of our setup. This is some of the sorbent degradation analysis. That's less important. The sorbent cycling was kind of what we based our decisions off of. And this one doesn't have our best curve on it. We can talk about it another time. But the reason that we went with fumed silica impregnated with polyethyleneamine was it had the highest working capacity across a range of desorption temperatures. We were able to get the most CO2 out of it, essentially. Mm-hmm. Its adsorption kinetics were quite slow as compared to Luatit's. And let me see if I can actually show you guys, because there's a particular graph that shows this analysis a lot better. And sorry, yeah, we'll put together all of our...
Yeah, we'll get it together. Ben, just real quick, one of the things that we did, which was kind of part of our brief, although this might change, is we just took that sorbent that we had, the zeolite, and we're able to just pour it into our sorbent chamber. David, I don't think there was any additional treatment of it, right? It was like just right out of the
just
bottle.
Poured it in.
Yeah. When you talked about the treatment you had to do with the silica fume one there and embedding it to create that particulate matter, what if you could just very briefly describe, like, what's that process like in a lab environment? Is it relatively easy to do, safe to do?
Yeah, no, for sure. That's like such an important question. The ability to synthesize these sorbents is a huge bottleneck. Was it easy? No. It took probably a week to synthesize 200 grams of the sorbent. We had to use some vacuum distillation. We needed a vacuum heating oven. We needed a serious amount of methanol. And if anyone's worked with methanol before, not the best stuff. And fumed silica itself, right? It's a nanoparticle that can like terrorize your lungs pretty easily. So in short, no, it's a really bad thing to work with. And I spent a lot of time trying to be as safe as possible in the lab doing that. And I don't know, Luatit is a way easier drop-in. To wrap this up, I'll be done here. This is kind of our most important graph. This shows the sorption capacity of these sorbents across different cycles. So the first cycle is a temperature swing of 60 degrees Celsius. The second one is a temperature cycle of 70 degrees Celsius, or sorry, I actually take that back. The maximum temperature we hit is 60 degrees Celsius for desorption, 70, 80, 90. And we only did up to 90 because degradation in oxygen happens after kind of 90 degrees C. And we can see that there's kind of decreasing returns here because we did these sorption cycles in series. There's no regeneration in between them.
Okay.
So it's not the best. We did what we could with the limited amount of time we had on the TGA. But you can see that FSPEI maintains the whole time the most ability to swing here across each one. And so you see when we go from 60 to 70, on 60, we cycle it twice at 60 and it goes down. And then we bump it up to 70. And now you've just unlocked a new sorption capacity and then decreases from there. And then you go to 80, increases briefly, lowers down again, and then increase again. You can see that pattern repeated across kind of all the sorbents. And there's a lot to kind of back out from this particular source of data. But you can see Luatit not performing amazing on that. That's part of the reason that we were a little bit less suspicious of this, but certainly this has been an analysis that was fairly prone to error. I would love to try and get into a lab and try and repeat some of this analysis. And for its purchasability and ease of use, I mean, I think Luatit is a pretty good drop-in idea. So
Ben,
sorry, I totally was just
No, that was great. That was awesome.
No, that was super interesting.
Really
Ben,
good.
when you talked about the you showed these, you did 4 cycles. So
Yeah.
but then you said something about you didn't regenerate them. What can you explain what you meant by that?
Yeah, so we did regenerate them, and I have to look at the actual experimental procedure, but we regenerated them for probably only 30 minutes in an ambient atmosphere. So we would ramp up our temperature, go through a desorption phase because the sorbents are, when they get loaded, are already adsorbed, fully sorbed. We would ramp it up to 60 degrees C, hold it there for I think 10 minutes, and I'll have to dig through exactly how we chose those time increments. Hold it there for 10 minutes, let it desorb across that time, measure the CO2 flux coming off of it, or in this case, our mass flux. And then, we take that mass flux and then back out that it was all CO2. That's an assumption that we made. And then set it back down to 25 degrees C and let it adsorb for about an hour, and then do that same process again. And so what that means, Tim, is that it didn't get to fully adsorb across each of those 60 minutes because you see that decreasing sorption capacity. It's also difficult because there's degradation happening at the same time. Both of those variables are confounding, but below 100 degrees C, we can make an assumption and say most of what we're seeing is just not complete sorption instead of degradation. Does that follow?
Yeah, I guess maybe. So are you saying that during these kind of regeneration cycles where you let it suck up more atmospheric CO2, was that half hour or however long it was more than enough for it to absorb as much CO2 as it could?
Yeah. So
you're saying that
you're exactly right. It's not enough time to fully adsorb.
Okay. All right.
Yeah. But yes, it is not enough time to fully adsorb. And so one thing that's interesting to note, we can see way faster kinetics with the Luatit. It picks back up CO2 far quicker than the fumed silica PEI did. But that said, it just had a far lower working capacity, right? The FSPEI essentially was just able to soak up way more CO2, way slower, but it just held a heck of a lot more CO2 than our Luatit did.
Okay, cool. David Ling, any questions that sort of pop out? I did want to put the picture just to put it in people's heads about what our design was. And off to the right here, you can see this is the sorbent panel, which we had the wires running through it that heated up, and then we just poured right out of the bottle into that box and then sealed it. That's how, and you'll in future optimizations about how to improve airflow. But David, any initial sort of thoughts or questions on what Ben has shared?
Yeah, I'm real curious about the machine that Ben used. Do you have a picture of it or a schematic of what was in it and how it worked?
Yeah, let's see here. Some of the prettier pictures I've uploaded into the Discord chat.
Yeah,
Let me see.
Okay.
I could try to find that.
Yeah. So those are the pretty ones. Those don't do too much for you in terms of schematic. I have one pulled up here. I can go back to sharing here real quick. But it's David. In short, it's super similar. We're both working pretty heavily from a basis of what the Thursday team members did. So it's pretty darn similar. I would say it's potentially the same thing, minus the ability to depressurize the main sorbent chamber. Are y'all able to see my screen currently? Oh, there we go.
Yeah, I was just showing this here is what you had shared. Was last
audience.
Yeah, very cool. And you had another one too. I don't know how to turn this off without screwing it up.
Has a mad scientist look to it.
It does.
Yeah. You were making it to be an art installation at the same time.
Yeah. So again, like some of the choices we made aren't purely functional. There's some kind of sculptural design elements, and so I toe this line for a device that really means like nothing to nobody. It doesn't mean much to an engineer. It doesn't mean too much to an artist. But I don't know. It's fun. I'm in love with the device. I really want to see what I do with it next. But certainly, it's kind of like, well, you created this thing, shipped it in an 80-pound duffel bag to China, had most of the components manufactured probably in China. And so like the embodied carbon emissions of this quote unquote carbon removal device, pretty insane. I want to do an LCA so that I can be quite honest and upfront about that. But future work.
Yeah, future work for us too. We kind of have the philosophy of let's start something here, not obsess too much over the LCA because that'll be a focus of optimization, but also don't put ourselves on a course where we're locked into something that can't possibly have a favorable life cycle analysis. So, but yeah, Ben, would love to merge efforts here, brother.
Yeah. No, yeah, super excited to kind of collaborate.
Well, I am of the mind of wanting to make at least the decision because it's not like there's no going back, just about what to test next. And there's a couple questions here that I'd like to ask everybody. One is what you described process-wise with the silica one sounds well beyond our parameters for safety and ease of use. So I think on that basis alone, I wouldn't sleep at night if I thought people were screwing around with that. But it sounds like, what do you guys, I mean, we can explore this a little bit more this week, but the Luitite sounds like a good option for us to just proceed with. And a question, David, is we have a guy, another member, this time doesn't work for him, who's at UPenn, who's an engineer, now that you're back in town as well, where we could order that and test it out with the build one and just see, right? But I'm curious what your thoughts are on that point and more generally on going with the Luitite.
I guess we could test it. We can't do any vacuum swing with it. We can just do temperature swing. If it's something that can happen this summer, I could help out with that. I'll be away and kind of unavailable for a couple of weeks. Would that work? I don't know. The whole system needs a boost in efficiency. Depends on what temperature we need it to get to. I'll think about that.
Okay. Again, we can bring in our new guy in Philadelphia who's a UPenn student to help with that as he's offered. So even if you're not available, as long as we have your brain that's able to look at, and we can talk to Peter and the team there as well. So that sounds very promising. And I have some funds to go ahead and do that. So why don't we take a few more days, chat it out a bit more. Ben, you can give some feedback, but I would love to at least see if we can solve that problem to see if we do get an improvement with it. I think would be great, and I'm ready to make the order if folks agree with it. But
Yeah, if I could have one kind of thought on that,
yeah,
I think that's great. Like I would love to try and test out Limited. My main question is, and again, I'm still green to this project, but what the kind of I don't know, what's the state of our sensors? Like what kind of accuracy and granularity can we get out of those sensors? Because one,
Yeah.
it'll be really cool to be able to see the degradation over time of luitit in exposure to atmosphere, right? Because that's something that will happen. And if we can characterize how poorly that's happening, that's going to be really, really important for us. And we need some pretty granular data to be able to do that. And
Yeah.
could you, David, could you run me through the sensors that we have currently?
well, we're just about at time, so we have a couple minutes to do that. But
True.
that is a thing that we are very much. If you go to that brief that I put there, there's 2 items that pertain to sensor upgrades and improvements. It's definitely a part of the whole here. But go ahead, David.
Yeah, we use the SCD. I forgot the part number already,
I
but
think it's 30. Oh yeah,
Yeah,
Seth and I talked
that's the
about.
that's the same one we used.
yeah, they were frustrating.
Yeah.
Maybe where they were mounted, and turbulence and stuff, but
Yep.
we were never sure what we were measuring, and so
Yeah, they have like a response time of like 3 minutes.
Yeah.
So Seth and I talked to the Sensorium person who said that like we should try this other one that has a response time of 90 seconds. So half the time.
These are we're located both here.
That's right on both the how you mount it to avoid any degree of turbulence with it, and that kind of it's activation time were 2 problems we ran into too. But it's possible we can get over that so long as right they're measuring accurately. Like we can, as long as we're doing long-term experiments, they'll eventually pick up the correct data.
So I have some stuff to say about the Sensorium, what the Sensorium person said. But also I want to mention before we have to like get kicked off of this call because Chris might be out of time. Seth can't get into the meeting at all, so he was forced to leave. He said that StreamYard didn't work for him.
Okay, we'll figure that out. It sounded like it was a work block that he had, but he's one of our key sensor guys, so he'll be involved in that. Anything else, Link?
Okay, so I'll just try to say it really fast. The rep basically said that these sensors are not meant for like fast changes in air quality, and they're supposed to be for like a room air quality. So like for a bunch of people who are standing in the room and then the air quality changes slowly, it's like meant for that. So we're kind of using it for the wrong purpose, but it's possible to like improve the performance. And then also the other sensor that we were looking at is not much different in price, and so we can just try that instead.
Yeah, I'm down for that if you guys think it's good. It sounded like what Seth laid out last week. It sounded like there was a real reason to kind of move forward in that direction, so we can go ahead and do that. So that could be two changes.
Yeah, I can make a post on Discord about sensors.
Yeah, put it on the forum if you could, and then it'll pop into the Discord. So, all right, cool. This was great. I feel like we made some progress, and I want to thank the now 34 people we have tuning in. We didn't advertise this, but it's great. Hopefully, this sparked some thinking. What I will do just to close real quick is again just direct your attention to the little brochure that we've made, the digital brochure, and encourage folks to really take a look at that. Unfortunately, I can't scroll right now, but it's got really good layout of more or less everything that we're looking to work on in addition to sorbent. Sorbent is just the first step, but we have all sorts of descriptive stuff in here, little videos of each of the upgrades we're trying to make. So if any of those sing to your DAC enthusiasm or general nerdiness, and you feel like you might have something to contribute, we would love to have more and more people involved in helping us think this through. So with that, we'll be back here next Monday. Please do join. Please do join our Discord and be a part of this. We want to get hundreds, if not thousands, of people involved. We want to be building these babies, all over the place after this summer. So thanks, team, and I'll see you guys on the Discord and on the forum. Have a good week. Great to have you back, David.
Thank you.
See ya.
Nice to be back. Bye.
Y'all